Welcome everyone. So we'll start within few minutes. Let others also join. Hello, am I audible now? Can anyone please confirm me? Karthikeya, can you please confirm me? Am I audible?
Yes, sir.
Yeah, okay. All right. Okay, yeah. So welcome everyone to the NPTEL session for the course Fluid Mechanics. So my name is Varnit Kapoor and I'll be the TA for this course, and I'll be taking this course throughout this semester. I'm pursuing my PhD from IIT Delhi. And during the course, if you have any doubts, any question at any point of time when I'm explaining, you can stop me and ask me at any point of time. Don't hesitate. All right. So let me just share my screen and let us start. So, all of you have watched the lecture videos by the professor on the portal?
Yes, sir.
You have watched?
Yes, sir,
Has
we have
anyone
watched.
done the assignment? Okay, great. Has anyone done the assignment as well? The first assignment? Okay, no problem. So just one thing to keep in mind, that uh, I just want that every one of you should be regular, because those who have enrolled for the course, either you are giving the exam or not. For giving exam, it is mandatory to complete all your assignments, as well as you have to give the exam at the NPTEL centers. And others who haven't registered for the course, so basically you have to at least be regular to your course, so it will helpful for all of you. And I expect that people are from civil or mechanical background here, who are who might have taken this course, the fluid mechanics. All right, let me share my screen and let us start. I hope my screen is visible. Is it visible?
Yes, sir, it is.
Okay, great. All right. So let us start with the topic itself. So our subject is fluid mechanics. So parallelly, you all can also write down the notes, whatever you want to write down. And additionally, I'll share this PDF of the notes after every session. Okay, whatever notes we are creating. Okay, so what does the term fluid mechanics tells you? So fluid, basically, you have in your environment, in the mother nature, that the fluid can exist in two forms, either liquid or gas. And what is mechanics? Mechanics basically tell that the word mechanics says that either it is a motion or it is in static. Okay, so fluid mechanics means a fluid which is under the motion or is in the static. So we'll cover a lot of topics here, like starting with the fluid properties, the pressure measurement devices. So what are fluid properties? Like density, specific weight, specific gravity, bulk modulus, compressibility of the fluid, surface tension, capillarity of the fluid. Okay, what are the pressure measurement devices available, like gauges or different kind of manometers, piezometers and all. Then there is a hydrostatic forces acting on the fluid, on because of the fluid on the substrate or on the walls. The other case is buoyancy. Okay, so how the fluid, solid object kept in a fluid, is able to float or sink because of the buoyant force presence or absence. Okay, then we'll cover the fluid kinematics topic, that how the fluid behaves in the motion. Okay, then we'll cover the fluid dynamics topics, where we will study about the forces over the net forces. Basically, it's Newton's second law, which we will describe. Then we'll cover the flow through pipes, where we'll cover laminar pipe flow, turbulent flows. Okay, so this is the whole brief overview which we will go through. So let me start with the fluid properties topic. Fluid properties. This one. Fluid properties. Okay. So first of all, as I said, fluid mechanics is a terminology which says that a fluid which is in rest or motion. Okay. So it is a science, basically. Fluid mechanics is a science that deals with the study of motion and rest condition on the fluid mass, like liquid or gas. So I'll write it here. It is a science fluid mechanics is a science which deals with study of motion and rest condition on the fluid of on the mass of on the mass of fluid. And what kind of fluid it can be? Gas and liquid. Gas and liquid. So it is a science which deals with the study of motion and rest condition on the mass of fluid. And fluid can be gas or liquid. Now, what is a fluid? We are saying fluid, 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 fluid everywhere. So this is basically nothing but fluid mechanics. So we are saying fluid mechanics, fluid everywhere. So what fluid actually is in the scientific term? So a fluid is nothing but a substance which is capable of flowing as well as deforming under action of shear forces, under the action of shear force. Okay. How, and it can the force can be of any value, either it's a very too large or even a small value of force you apply. Okay. Whereas what is a solid? In solids, deformation is almost negligible. Okay. So suppose I have this pen. So if I want to provide a shear force, like I want to pull it like this, so deformation is negligible. Whereas if you just pull a surface of the water, there will be a change in the fluid. There will be a deformation as well as fluid will also flow. Okay. So let me write it here. What is fluid? I'll explain with examples as well. Yeah. And I'll be writing the notes very detailed. So a fluid is a substance which is capable of flowing and deforming under action of shear force, and that force can be however small it can be. However, shear force, I'm saying force, however small force can be. All right. Whereas a solid deformation is almost, so here, which is capable of flowing and deforming. Keep these two words in mind. A solid deformation is almost constant, but in fluid, it changes with time. It changes with time. So in the fluids, we, because deformation is changing with time. So what word will come? The word will come rate of change. Okay. With respect to time, something is happening that describes the rate of that event to occur. Okay. So so I was saying with time, so in fluids, rate of deformation. So in the fluids, rate of deformation is more important. So rate of deformation is more important. Always remember, rate of the deformation is important in the fluids. More important than deformation. Than deformation. I'll highlight this. The rate of deformation is important in fluids compared to the deformation itself. Let us understand with some basic example. So suppose I have a block, okay, and this is a wall, right? And this is a block kept over the wall, solid block, all right? This is a solid block. If I give a shear stress, what do I mean by shear stress? That I'm parallel to the plane of that object. If I'm providing a shear force or shear stress, right, like this, shear force, a parallel to the plane force applied to the solid object, what will happen? Eventually, the solid should turn from this to this, from horizontal, vertical to a slight incline, okay? Vertical to slight incline. So what's gonna happen to the object? It's gonna like a slight shift, okay? Like this. there will be a slight shift. So what we observe, there is some angle or deformation has happened here. Phi. Phi is the deformation, and more the amount of force you apply at the top, the more the deformation will occur. But you observe that the deformation is constant at a particular instant. Okay, so what we can say here is that shear stress is proportional to nothing but phi. That is your angle, or you can say the deformation. If it is something is some quantity is proportional to other quantity, this can be written as tau is equal to some constant g times phi, some constant g times phi. So g is nothing but a modulus of that object tau by phi, nothing but tau by phi, which defines a modulus of that object, a property of an object. Property is something fixed for a particular object. All right. So you know that water has a density of 1,000. A solid block of some say wood has some constant density. So it will have another kind of constant property, that is G. Okay, we'll come to that what we term it like that. So G is nothing but tau by phi for the solid. So I'm currently talking about solids. Solid. This is a solid object. So G is nothing but tau by phi. What if I say tau is 0? Let us take some case where my tau is 0. If my tau is 0, what will be G? What will be G? Anyone can tell me? If my tau is 0, what will be G? G will be 0. But is it possible? No. That means you are not providing any shear force. What if my tau is non-zero? Suppose I say tau is non-zero and G is infinite. That the solid object has a property which can resist infinite amount of this, so that there is no deformation. This solid is not at all deforming. Then what happens? Phi is 0 in that case. If you put mathematically, let's see, if you put phi as 0, what will be G? It will be infinite. Mathematically also understand, physically also understand. If a G is infinite, a solid object is like it has infinite amount of strength, and it is whatever force you apply with a machine, with your hands, with anything, that object is not gonna deform at all. Okay, so there in that and practically there is no such object on our planet which cannot be deformed. There is some kind of deformation. So G is constant here for a particular property, for a particular solid. And you also see the stress strain curve. I don't know, you have studied strength of material so far, so you might have seen a stress strain curve like this. Let me take the shape. So if I say this is a shear stress versus strain, okay, so you might see in future in your courses, or you might have seen for a object, for a solid object, it will something look like this, a maximum point of strength, and then it will fracture. Okay, so during the linear phenomena which is happening till here, suppose, so linear phenomena is happening here. So what you observe that for a particular phi 1, there is a tau 1. For a particular shear stress, there is a particular deformation. For another particular shear stress, there is another deformation, okay, which is linearly changing. That is why I chose this relation. Tau is directly proportional to phi. Okay. All right. So this was all about solid. Now let's come to the fluid, which is our main purpose. Because I wrote here, we are interested in the rate of deformation in fluids, not the deformation. So what will happen to a fluid? Suppose let us take fluid. Again, I have an element, a fluid element this time. So this is my wall, and there is some fluid element, let us say like this. This is a fluid element. Now, if you provide shear force or shear stress to the top surface of the fluid, what's going to happen? Will there be a constant deformation, or will there be a continuous deformation? Mark my words. Will there be a constant deformation or continuous deformation in the fluid? It will be, anyone can answer? You all can unmute. I need the session to be interactive if you want. Don't hesitate whether you are right. Yeah.
Continuous deformation.
Continuous deformation. Correct. Exactly. Perfect. The deformation will be continuous happening in the fluid. So what's going to happen? So my fluid will look like this. So like this, for one point, for other point, like this. And similar thing is going to happen till here. Like this, and like this. With the same amount. Okay. Whatever is the case here. So here it is phi 1. Let me take it out here. This angle is phi 1. This angle is phi 2. And this angle is phi 3. Okay. So all of them are unequal and can be equal depending on the object symmetry, fluid element symmetry. But this phi 1 will be equal to this phi 1. Then that phi 2 will be equal to this phi 2. Similarly, phi 3. Always well. Okay. So now what we are interested in, our shear stress is not only directionally proportional to the shear strain, it's also proportional to inverse of time. Okay. Inverse of time. That means for fluids, you are interested in deformation with respect to time. And when the element is small, then your shear is nothing but the change in the deformation with respect to time. Change in the rate, and this is nothing but your rate of shear strain. This is nothing but rate of shear strain. Okay, this is nothing but the rate of shear strain. And if something is proportional to some quantity, you can write in the form of tau is equal to some mu d phi by dt. And mu is now again the property for fluid, not solid. G was the property for solid, mu is the property of fluid. And mu is nothing but, if you observe here in this, mu is inversely proportional to d phi by dt. So what is mu? Mu is, we can say that it is called as viscosity of the fluid. You see now, you have a water and you have a honey. Which one is more viscous you feel? When you put it on your hand, the water will flow it easily on your hand. Whereas if you put honey between your fingers, it will be a much thicker. And what defines the difference between two of them is physically is that the viscosity, the viscous nature of the fluid. So honey cannot be deformed very easily. Honey cannot be deformed. That is why rate of deformation is less in honey. So its viscosity is high. So when the rate of deformation is less, then viscosity is high. If rate of deformation is more, like in water, then viscosity will be low. Water has a lower viscosity compared to a honey. Okay. So what I can write? What I can write is that here mu is coefficient of the viscosity, okay, of that fluid. So here mu is the coefficient. There G was constant value. Okay. And d phi by dt, that is your rate of deformation, is inversely proportional to the viscosity. So a more rate of deformation. So if d phi by dt in the first fluid is more than d phi by dt in the second fluid, that means your viscosity of first fluid is less than viscosity of second. Okay. Example can be honey. So this is nothing but your water, and this is nothing but your honey. All right, water and honey. I hope it is very crystal clear that what is viscosity, what is rate of deformation, what is deformation, what fluid is, what solid is, at a very basic level. So I'll make a table here between comparison of solid and fluid. Now, in some another perspective, I want to show you. That's very important table. So we'll write note here. Note. So first is solid, and other is solid versus liquid. After understanding this, what we can say, the first point is that a solid can resist your tensile. If a solid, if you provide a force equal and opposite to the solid, it will not move. Suppose this is my pencil. If I pull from both the sides, what's going to happen? It's staying at rest. Nothing is going to change. Or even if I compress it, is it bending? No. Is it moving? No. So it is at rest. So first thing is that if you provide a tensile force, not shear force. Okay. So my solid object is like this. Either I provide compressive force or I provide a tensile force, stretching force, sigma and sigma. So in both the cases, my object is always going to be at rest. At rest. Okay, for the solid. Whereas if you go for the liquid, you have a liquid element. Okay, and when you try to stretch the liquid element, liquid element have particles inside it. Okay, like this. There are two liquid particles. Is it gonna resist the motion? Resist the stretching or not? Tell me, is it gonna resist the stretching?
No, sir.
If you are stretching a fluid, no, it is not gonna resist the stretching. So it will get easily pulled. Your fluid can get easily pulled. Okay, so the resistance is negligible. Okay, whereas when I give a case for the fluid where I am compressing, giving a compressive force over that element with a pressure P on the fluid, it acts as a pressure P. Sigma is nothing but your P here. Okay, is the fluid gonna compress or not? Or maybe both can be happen? Please tell me. Is the fluid gonna compress or it cannot, or both ways? So when you try to compress a fluid, okay, maybe fluid can be if a fluid is liquid, maybe it won't compress that much, a little bit. Whereas if it's a fluid is gas, easily it's gonna compress. Okay, so that means it can a fluid can be compressible as well as incompressible. In our case, we are taking a liquid, so we can say that the element will be at rest as well as it is not compressing, so it is incompressible. And the fluid is at rest. Okay, next case between solid and fluid is that second point. If I'm providing a shears that we have seen, if there is a solid block and I'm providing a shear force tau, obviously the object is going to be at rest. It won't move. Okay, it can deform, but it won't move. All right, until unless I give a pushing force. Totally. So there's a chance that it won't move. So it's a condition called as the rest, but it can deform. Whereas if there's a fluid element with me and I'm providing a shear force, it will deform as well as be in motion. It is flowable as well as deform with time, that is rate of deformation. So if you have two molecules here, suppose like this, they are gonna deform with the shear stress and gonna be in motion as well. So the property of this defines is mu, that is viscosity of that. So I'll write a point here. A solid can resist tensile, compressive, and shear forces. So if you observe here, this condition was also rest, this condition was also rest for the solid. For and shear forces under static condition. What does it mean? Static condition. If the object was initially at rest, then it's gonna be at rest only under static condition, and it obeys the from mechanics point of view. You can see it's a Newton's which law? First, second, or third? Tell me. You might have studied at your school level. Yes. Which law?
First law, Newton's first law.
First law. If an object is at rest, it will be in rest. If an object is in motion, it will be in motion. Okay, simple. Whereas fluids have negligible resistance. Fluids will have negligible resistance for tensile loads. If you are stretching, resistance is negligible. Tensile loads, they resist compressive forces. After a certain extent, you cannot compress a fluid. Okay, resist compressive forces. Due to bulk modulus of the fluid, I'll explain this bulk modulus, every terminology will come, don't worry. Due to bulk modulus of fluid, and they resist the shear forces under and don't worry about notes. Notes will be shared with you. These notes I'll share with you after the session on the portal, as well as I'll be uploading these recordings as well on my YouTube channel. So if someone was late, don't worry, you can catch up from there as well, but you attend here. Okay, shear forces, if you forgot something you're not able to understand, you can repeat and see those videos as well. Forces under, so session is recording, don't worry about it. Under dynamic, just focus on learning dynamic condition due to viscosity of fluid. Okay, so when you are providing a shear, then viscosity will play a role. When you are providing a compression, then a bulk modulus defined by K, a bulk modulus will play a role. Okay, the property of bulk modulus will play a role. All right, any doubts still here to anyone? No doubts? Great. Now let's come to the topic, concept of continuum. Concept of continuum. Okay. You say we have heard this word continuum, but we don't know what actually it is. Anyone knows what is continuum? The word itself tells what it will mean. Anyone of you can unmute and tell me. What is continuum? Anyone? No idea? So continuum from the word itself is nothing but continuous. Something continuous is happening. Okay. So when there is a viscous fluid, okay, whenever there is a viscosity in the fluid which flow over surface, then the bulk of the fluid sticks over that surface. Okay, always. So we are talking about the bulk phenomena. Bulk phenomena or continuous phenomena is nothing but the concept of continuum. So suppose I have a, I'll make like this. I have a fluid flowing through this pipe. Okay, this is a pipe and fluid is flowing through it. So what will I do? I'll first of all create a control volume under which I can understand. Okay, so control volume is like, I define a boundary to that flow of the fluid, and eventually the fluid will have particles, okay, in which there is forces are happening, in which forces are happening. So this is your control volume. and the length of this much. The length of this is LC, and it is called as characteristic length. Characteristic length of the control volume. The control volume is nothing but it's an open system kind of thing. So you might have heard about closed system and open system in your thermodynamics course. So open system is nothing but where mass as well as energy interaction is taking place, and closed system is something where only energy interaction takes place, mass is totally observed. But here this is an open system of water is flowing through the pipe, so it's continuously flowing through. Okay, so you have to take some, whenever you are dealing with an open system scenarios, you have to take a control volume, define a boundary, and inside that boundary, that is your whole system, and inside that boundary you will do your study. So whatever boundary you are considering, it will have some length. Okay, so by length I don't mean that it's a cuboid kind of thing, so length into breadth into height. It is not like that. By length mean it's a something a parameter which define the length of cumulative length of that scenario of that control point. Okay, that's why I say it is a characteristic length. Okay, it's not the actual length you are saying about. So characteristic length so characteristic length, if the bonding, so eventually there is a I'll write that. There is some distance between the fluid particles. There is some distance between the fluid particles. This distance marked in the red. So this is nothing but mean free path. You might have heard this word, mean free path. Okay, that is nothing but a path between which the molecules can easily move. Okay, so if a scenario comes out that your mean free path lambda, I denote with the symbol lambda, if your mean free path is greater than the characteristic length of your system, is greater than the characteristic length LC of your system, what's going to happen? That means, let me help you to visualize. So this is the mean free path between the two particles, and your characteristic length of this you have taken the system is this much, LC. Okay, does these two particles come under your system, the control volume? Are these two particles inside your control volume? Please tell me yes or no. I want a yes or no from all of you.
No, sir.
No, right? The fluid particles are not inside the control volume. That means your mean free path is greater than the characteristic length. So here you cannot define the concept of continuum. Okay, you cannot define the concept of continuum here because you cannot define any part. There are no particles inside this. Okay, particles are outside the system control volume which you have defined. So that means concept of continuum will not be valid when your mean free path is greater than the characteristic length. Okay, it will only be valid when in this scenario where your characteristic length is greater than the mean free path, is greater than the mean free path. Then only you can say that yes, I have molecules inside it, and I will say that all of these molecules are continuous in nature in whole inside this control volume. Okay, so I'll define one control volume. All the particles inside the control volume are there, and for all of these particles, I'll say that I'll give a fluid property, fluid velocity, the terminologies for this whole control volume instead of one single molecule inside. This is nothing but your concept of continuum. This is nothing but your concept of continuum. So at mathematical level, at physical level, I think I'm able to explain. Any doubts in understanding, please tell. So I'll make a graph. Here. Very important concept I have explained you in an easy manner. Lot of people till the end of their graduation don't understand what is concept of continuum. And I'm serious, they don't understand. So this is the property density, and this is suppose some volume V of that fluid, of the control volume. So where my concept of continuum will happen, so I'll make this. So if my this scenario, lambda is greater than LC. That is, lambda is your mean free path, is greater than the characteristic length. Obviously, concept of continuum is not valid. The concept of continuum will only be valid outside this when your lambda is less than LC. So validity of continuum starts from this point. This is your point where validity of continuum starts. Now it's your choice. Whatever the amount of length you want to take, you can take this much LC or you can take this much of LC. That depends on you. That you want to say my continuous particles are between this much, or the earlier case only this much. That's your choice as per your system's requirement. Okay. Okay, I think it's very easy. What is concept of continuum? Okay. Now, when there is a viscous fluid which flows over the surface, okay, you have a table or something, and you put a fluid over it. So what happens? You observe that some fluid is sticking on that surface. Okay, you observe that most of the fluid will pass away, but still few drops of the fluid will remain there on the surface. Okay, this because of this it acquires the fluid acquires the velocity of the surface, and surface what initially at rest. So if you have a table and you pour a water and you throw a water out of it, my hand is unstable. So some droplets which were there, they will be at rest. They will now come at rest, whereas most of the fluid goes up. So the particles which are at rest, those who have attained the speed of this hand, that is your scenario where the fluid particles come at the speed of the table. If the table is also moving and particles also stick, both will have same velocity. If the table is no relative velocity between them. If the table is still and particle also is on there, it is also stick, then velocity is 0. Okay. So this condition is called as no slip phenomena. The fluid particles which are stick over the surface are not slipping now. This phenomenon is called as no slip phenomena, and it will only and only be valid under the concept validity of continuum. Only be valid under the concept of continuum, not outside the concept of continuum. Always remember that. So I'll write this point. When viscous fluid flows over surface, then what happens? Bulk of fluid sticks. It is sticking, not adhesion. It is not pasted. It is just stick. If you put up more force, it will get removed as well. Okay. So it is sticking, not adhesion. Not adhesion. Over the surface. Due to that, it will acquire surface velocity. And this phenomena is known as very important phenomena. You are going to hear this word a multiple number of times. Is known as no slip phenomenon. No slip phenomenon. And it is defined by concept of continuum. Okay, so I'll make a diagram here. So suppose I have a surface here, and the fluid comes from this side. Use the blue color for fluid. A fluid is coming from the left to right. The fluid has some viscosity, and some initial velocity. We call it as U infinite. U infinite. So what's going to happen? Most of the fluid will pass away, but some layer of the fluid at the surface, which will have some particles, that is bulk of particles, will stick to the surface. And this situation is known as no slip. The particles have come to rest. Okay. Now, this was a case of water, but you have seen that mercury, if you have seen an element mercury, it doesn't stick easily on the surface. You have seen that it is have very high cohesion compared to adhesion. Okay. Even if you put your finger, it will separate, move aside, or whatever you put on the table, it will roll like some few particles. Okay. So, but I understand that there is a cohesion, and still, if you throw a mercury fluid, then also some particles will remain there as well. However, amount of high cohesion between the intermolecular forces of the mercury are, still few drops, 1 or 2 drops will be there. Okay, so that means no slip phenomena is valid in the concept of continuum in the real world scenario every. Okay, all right. So I'll write a simple point here that for mercury, I'll denote mercury with the symbol Hg. Okay. For mercury, also no slip is valid. Okay. Any doubts still here? We are finished with this concept of continuum. Any doubts, please? Feel free to ask if you have any doubts. Any doubts? Yes, no, please say something.
No doubt, sir.
No doubts? Great. Take a minute, whatever you have written or understood, just either you see your notes, or if you have not written so far, just close your eyes and think that what we have done. Take a minute or two. Take it as a short break, or to just remember the things. I'll just be back in a minute or two. Okay, please just wait. Thank you. I'll be back in a minute or two. All right. Okay, that's very quick. Now let's come to another topic. That is nothing but fluid density. Fluid density, or we also call it as mass density of the fluid. What is the density? What is density? Anyone? What is density?
Mass per unit volume, sir.
Mass per unit. Correct. This is correct. It is mass per unit volume, but there is a little addition. Mass per unit volume at a particular pressure and temperature. Density is nothing but mass per unit volume at a particular pressure and temperature. So if any of the term, either pressure changes or temperature changes or both changes, your density is going to change. Okay, always remember. So let me write here. It is defined as mass per unit volume at specific pressure and temperature. So even a water can have different densities depending on it is kept in the room temperature or some, you can say, evaporator where, or in a pan, boiling pan, the density will change there. So density symbol we defined as a rho. So density is mass to that of volume, and the unit of density is nothing but in SI kg per, because mass is in kg and volume is in meter cube. Example. So what are the examples? If you have a pressure of 1 atmosphere and temperature is 0 degrees Celsius, 1 atmosphere of pressure and 0 degrees Celsius of temperature, then density of water is 1000 kg per meter cube. Okay. But if you have 1 atmosphere, pressure is same, but temperature is changed to 20 degrees Celsius, then your density of water will be slightly lower, 998 kg per meter cube. Another scenario, if your pressure is changed and temperature is remaining fixed. So I increase the pressure, suppose by 100 times, and temperature is 20 degrees Celsius. Then what is happening? Density of water, I'll use symbol W now this time, will be a higher 1003 kg per meter cube. So what we have observed, this is a scenario where P was fixed initially, then temperature was changed. Then pressure was changed and temperature was fixed. Okay, this was a scenario 4. All right. You have to always remember that 1 atmosphere and 20 degrees Celsius, density of water is 998, very important. In the question, it will be coming like this only. Water at the 1 atmosphere and 20 degrees Celsius. That means you have to remember this term. And for similarly for air, 1 atmosphere and 20 degrees Celsius, density of air is 1.23 kg per meter cube. But if I say my pressure has increased to 100 atmosphere, okay, and my temperature is also changed to 0 degrees Celsius, then density of air is 1.27 kg per meter cube. And this is a STP condition, okay, standard temperature conditions. So this and this value, you will see most common, 1 atmosphere, 20 degrees Celsius, because these are the room conditions. Okay, room conditions. Okay. Now let's come to the next topic. Specific weight or weight density. Or you call it as weight density. And its symbol is small omega. Small w, small omega, whatever. What is specific weight or weight density? So it is nothing but weight of the fluid with respect to the volume. Earlier, density was mass with respect to volume. Weight, specific weight itself has a term called as weight. So it will be weight per unit volume. Earlier it was mass per unit volume, it is weight per unit. So W, so it is weight of the fluid with respect to volume. So where I'm writing with respect to, I'll from now onwards I'll write the short notation WRT with respect to volume. Okay. So your small w is nothing but weight weight WT to that of volume, and weight is nothing but m into g. mg is your weight. When you multiply mass with the gravitational constant, is your weight with respect to volume. So it is not mass per unit volume is density. So you can also write it as rho into g. Very important. Okay. So and sometimes you will see in questions they won't give directly the density. They will give specific weight. And what is specific weight? We forget the term sometimes. So specific weight is rho times g. So from there you need to calculate density. They will give you omega. You know gravity at Earth is 9.81. You have to calculate rho from it. Okay. So what is specific weight of water? Example. Let us take some example. Your specific weight of water is, again at normal temperature condition. If you see your 1000 into 9.81, so it will be 9810. And what will be SI unit? Because it is weight, so it will be Newton. 9810 Newton per meter. Okay. mg is in Newton. And for air it is 1000 kgf per meter cube. It is an MKS unit. You have to remember this term. kgf per meter cube. This was an SI. And next one is an MKS unit. And what is 1 kgf? I'll write here. 1 kgf is nothing but 9.81 Newton per meter cube. So if you want this to be in SI, what you will do? 1000, sorry, it is not for here. My mistake, it is for water only. Both in SI and MKS I'm writing. So 1 kgf is 9.81. So you will multiply with 9.81. So it will be again 9810 kg per meter cube. Okay. So that is same again in SI. Okay. It's clear what is specific weight or weight density. It is weight per unit volume. That is rho g. Now what is relative density? All these terms you have to understand, because in the question they won't directly give you density. They will trick you. They will give you specific weight or weight density, relative density or specific gravity. These terms will come. So next is relative density. So as the term says relative, again, it is with respect one fluid with respect to another fluid. So it is nothing but density of one fluid with respect to density of another. So suppose they give you a relative density of 0.3 and they give you density of fluid 2. What is density of fluid 1? Okay, you have to calculate. Next is specific gravity. This is also very important term. Specific gravity. Specific gravity. So specific gravity is defined for a fluid Sg. For the fluid is defined as density of that fluid to that of density of standard fluid. What is standard fluid? So when it is a case of liquids, your standard fluid is water. In liquid, it is water. Rho is equal to rho of water. That is 1000 kg per meter cube. Whereas if it is a gas, then it will be rho will be equal to rho of air, and that is nothing but 1.27 kg per meter. Okay. Clear? Any doubts? Any doubts?
No, sir.
No doubts. Okay, great. Now, specific gravity of a fluid, as I said, it is nothing but density of that fluid to that of density of water when I'm understanding. If I multiply both numerator and denominator by G, what it will become? It will be specific weight of that fluid with respect to specific weight of water or the standard fluid. So specific gravity can also be written in this term, in terms of specific weights. Okay, this is also very important. So they'll try to trick you. Examiners will try to trick you in this. Question will be very easy, but they'll trick you by just giving specific gravity in terms of specific weights. So students get confused. What's happening? So let's take some example. Suppose specific gravity of mercury is given to be 13.6. Then it means specific weight of mercury to that of specific weight of water is 13.6. Okay. So this implies specific weight of mercury is 13.6 times of specific weight of water. Okay. So for a given volume of mercury, there are 13.6 times molecules of bombardment compared to that of water. 13.6 times bombardment is happening when the molecule, when you have two molecules. Suppose you have few molecules of water and some bombardment is happening. For mercury, it will be 13.6 times higher. Okay. Next example. Specific weight, specific gravity of gasoline is given as density of gasoline with that of density of air. Oh, sorry, density of water. Now, question will be there that gasoline is gas. Why we are taking standard fluid as water? Gasoline is not gas. Actually, it's in liquid form and compressed. Then compressed to a liquid form. Always, it's not always available in gaseous form. So gasoline is something. That's why I wrote this example. Whenever you see a word gasoline, then the standard fluid is water. That is a case of liquid, not gas. So what is density of gas? Suppose you have a density of gas, gasoline as 750 and density of water is 1000. So it will be 0.75. Specific gravity of gasoline will be gasoline. Gasoline. That's why I'm writing completely. So gasoline is liquid, not water, not gas. Okay, any doubts? Any doubts? Other students are not active?
No, sir.
Karthikeya, any doubts?
No doubts, sir. No doubts.
Naman? Naman is there? Suryansh?
No, sir.
Saurav?
No, sir.
Great, great. So anyone is from IIT during their graduation? IIT, NITs? Raise your hands. You can use raise hand option or state government universities. Any one of you? Oh, great. Suryansh, you are from which university?
Sir, I am from NIT Srinagar.
NIT Srinagar. Very beautiful place.
Yes,
Okay,
sir.
you might be enjoying there. Yeah, great. So everyone is in their BTech second year? Hopefully second year,
Yes,
I
sir.
expect. Right? Second year. All are from civil or some mechanical also there? Mechanical guys?
Some mechanical also.
So who is in mechanical? Raise your hand. You can use the raise hand option. Okay. One guy from, okay. All right, great. Others are from civil. Okay. But more or less, the syllabus is same for both cases. Okay. I see Saurav is also from. Great. All right. So let me start with the next topic, that is viscosity. I told you now I will be discussing what is viscosity. Every term I'll discuss in very, very detail. Okay. Because these are basics. Once your basics are formed, then you can easily handle the advanced things. But if your basics will be weak, then surely you will get confused. So what is viscosity? Viscosity, again, a property of a fluid which offer resistance between two adjacent layers of that fluid. Okay. So in fluid, viscosity is because of two things. One is the cohesive forces, and other is because of the molecular momentum transfer between the layers. Okay. So suppose you have a fluid like this, complete fluid, and fluid is in the form of layers. Okay. Have a fluid and it's in the form of layers. So suppose I choose this layer and this layer. So there will be some resistance happening between the two layers. Okay. And that is nothing but your viscosity. When there is a resistance between two adjacent layers, two adjacent, not this and this you are saying. Two adjacent mean together, adjacent to each other. Okay? Two adjacent. Then it is the property which is nothing but your viscosity. The property of fluid which offers the resistance between two adjacent layers. Why this viscosity happens? It is because of the cohesive forces or the molecular momentum transfer. In fluids, viscosity is due to first reason is cohesive forces in the liquids. Cohesive means intermolecular bonds force of between the particles. That is cohesion. And adhesion is nothing but between two different kind of objects. Either it's liquid, water, liquid, solid, 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 or liquid. Okay. Cohesive forces in liquids. And second is molecular momentum transfer between two adjacent layers. That is perpendicular in perpendicular direction. Perpendicular, not right. So molecular momentum transfer will happen in perpendicular direction. And where you will observe this molecular momentum in gases, where you will observe cohesions in liquids. Okay. So this is in gases. Okay. Cohesion is in liquids. Molecular momentum is in gases. Any doubts? No doubts. Okay. So that means viscosity is defined both for liquid and gas. But the phenomena in liquid and gas is different. Why the viscosity happens? So in liquid, it is cohesive forces between the two parallel planes, two parallel layers, whereas in gases, it's because of the molecular momentum transfer perpendicular to the parallel planes. So it's defined for liquid and for gas. Liquid. First of all, let's start with liquid. So suppose you have a wall like this. Okay. The fluid is coming from here. Fluid that is liquid is coming from here. Let me again make this type of this. Like this. And the liquid is coming from here. So liquid is coming in form of particles. Molecules will be there eventually. Okay, and it is coming at velocity that is u infinity. Okay, so eventually there is some bond forces between the molecules, between this molecule, this molecule, this molecule, this molecule, this molecule, this molecule. Okay, this is nothing but your cohesion forces between the molecules. So these are cohesion forces. Cohesion. Okay. Now these particles, fluid molecules, move further as well. So what is happening? This particle, and the particle which is near to the wall. Okay, particle which is near to the wall here is gonna face which condition? Which condition the particle will face, which is near to the wall?
No slip condition, sir.
No slip
No
condition.
slip condition.
Correct? No slip condition. Great. No slip condition. Whereas the other particles are still flowing. Okay. Particles are flowing. So here a layer will form of no slip. Here a layer will form of no slip. But what will happen when there is some resistance happening? So there is a cohesion between this as well as in this. Okay. Cohesion is happening between both the particles as well as this has cohesion with this as well as with this. Are you able to visualize? Okay. So what's happening here? Eventually, what is happening? That a single particle, this particle, if you consider it initially, this particle had cohesion between this particle and this particle. Then this particle has a cohesion between this particle and this particle. Then further, this particle will have a collision between this particle and this particle. So what is happening? It is trying to arrest the motion of the upward particles. So every above particle will move with some slower velocity compared to the upper particle. Compared to the upper vertical particle, the particle at the angle will be having a slower velocity compared to the lower particle. Oh, sorry, upper particle. Okay. So what is happening? Some formation of a layer of fluid is creating. Some formation of a layer of fluid is creating. And that is the resistance, which is not allowing full fluid to flow completely. Whatever fluid was coming from here, whatever fluid was coming from here is not completely flowing in the right side. Some fluid is getting trapped inside some layer because of the resistance. That resistance is your viscosity, and that happens because of the resistance between two adjacent layers, all between two adjacent layers. And this layer, and this layer, then this layer. Between every adjacent layer, this resistance is coming. Because of which layer is forming of fluid. That is your viscosity nature of that. I'll make a neat diagram. So another what is happening? Some layer is okay. Some layer is free. So here particle is free, but inside particle is not free. It will be somewhat like here. Okay. So these particles are moving with some another velocity, whereas these particles stay moving with u infinity. But here some u will come. Here some u will come. Here it will no slip. There's no slip. Velocity is 0. Here no slip. U is 0. Here it is u1. Here it is u2. Okay. I hope it is clear. So as temperature increases, what happens to the intermolecular forces in the liquids? Please tell me, what happens to the intermolecular forces between the liquids? They will increase
Sir,
or
they will
decrease?
break.
They will break, correct? That is why liquids evaporate into the form of gases. The intermolecular forces will break. That is nothing but cohesion. Cohesion will break. If cohesion will break, what does it mean? The viscosity is going to increase or decrease? The resistance is going to increase or decrease?
Decrease, sir.
Decrease.
Decrease.
Resistance is going to decrease. And if resistance is decreasing, that means viscosity is decreasing. That means viscosity is decreasing. So this is your resistance. All right. These are your resistances. If your temperature is increasing, if temperature increases, what happens to the cohesive forces? They decreases. This implies cohesive forces decreases. What does it mean? Your eventually viscosity decreases. Your viscosity decreases. So with the increase in temperature, viscosity decreases in case of liquids. In case of liquids. Clear?
Yes, sir.
Clear physical phenomena, right? Very simple to understand, but very difficult. Most of the students pass and they still don't able to visualize, because fluid you cannot visualize from your naked eye directly what is happening between the layers. You have to understand at the molecular level. Now comes to the gas. Now let's come to the gas. What is happening in the gas? So suppose I again make a velocity distribution plot. This is not axis. These are not axes. Just I'm making, this is a plate. And this depict velocities, okay, in vertical direction. What's happening? So what's happening? Similar kind of curve will be there. So here you suppose this is a plate. This is a velocity distribution. So again, in the gases also similar kind of thing will happen. So this will be at some velocity u. And again, the next adjacent layer will be at a velocity u plus du, some incremented velocity. Okay. But if you observe this layer 1 and 2, this layer 1 and this layer 2, how the molecular transfer happened in gas? It was not because of the cohesion, because intermolecular forces are very weak in gas. They are very negligible. It doesn't make a sense. Instead of that, the resistance is because of the molecular momentum transfer. That is, if you have a particle 1 here, molecule 1 here, and you have a molecule 2 here, let me use another color. If you have molecule 2 here, okay, so first molecule is transferring its momentum to the 2, and similarly 2 will also transfer equal momentum to the 1. Why? Newton's third law need to be valid. Okay, every action has equal and opposite reaction. So momentum will be balanced. Momentum will be balanced. Whatever momentum is transferred by 1 to 2, by 1 to 2, similar momentum will be transferred by 2 to 2. Okay, and that is causing resistance between the adjacent layers. And this is your randomness, because gas particles are moving very fast, very fast. Okay, and sometimes gas particles are so away that your characteristic length is shorter than the mean free path, because the path between the two molecules of the gas is very high and your characteristic length is slow. Then there the concept of continuum will be invalid. You have to connect your dots like this, that if a examiner is asking like this, then how will the concept of continuum will be valid if the mean free path is greater than the characteristic length? Assertion reason will come. What you will do? You have to answer like this. Okay. So what will happen if I increase the temperature? What will happen? What will happen to the randomness? Will the randomness increase or decrease?
So increase.
Increase. Correct. Randomness will increase because I'm giving more energy. So this is nothing but your randomness. So as I increase the temperature, if temperature is increased, this implies a randomness between the gas molecules will also increase. That means your root mean square velocity, because as per kinetic theory of gases, your root mean square velocity also increases. That means your viscosity also of the gas, here it was liquid and here it is gas also. So with the increase of temperature, viscosity increases in gases, whereas it was opposite in case of liquids. And I'll prove it mathematically also. This was the physical sense. This was a physical flavor to understand. But what will be the mathematical theory? So as per the kinetic theory of gases, you know that kinetic energy, what is the formula of kinetic energy? It is half mv RMS square, as well as with respect to temperature, kinetic energy is defined as 3/2 K times temperature. K is the Boltzmann constant. Compare both of them. Half mv square RMS square is equal to 3/2 kT. So basically mass is constant, 1/2, 3/2 are the constant, Boltzmann K is also constant. Only proportion is V RMS square is directly proportional to temperature. That means root mean square velocity is directly proportional to under. So with the increase of temperature, velocity increases, randomness increases, viscosity increases. So this implies E of gas also. Clear? Any doubts? Any doubts to anyone? Please ask if you have any doubts.
Sir, please explain once more.
Which case? Liquid or gas?
Gas.
Gas. So what is happening? You have layer 1, layer 2 in the case of gas. You have layer 1. I'll use this pen. You have layer 1, you have layer 2. The molecular momentum is transferring from one particle from one or molecule from one layer to the second layer. Similarly, 2 is also transferring to the one the same amount of momentum. So here something randomness is happening. Randomness is happening between the layers of the particle, and this randomness is perpendicular to the layers. This randomness is in the perpendicular direction to the fluid layer. Okay. So what happens because of that? Randomness increases, molecular momentum transfer. It provides a resistance. Because suppose you are, take an example. You are in a crowded area. You try to run, but there is so much of crowd. There is so much of randomness in the place. How you will be able to move? You will either push the person, or you will try to pass through the voids. That is nothing but your randomness. Okay. So randomness increases. Randomness increases because I say temperature also increase. Sun is at 50 degrees Celsius compared to the sun at 25 degrees Celsius, which will be a more uncomfortable condition for you. 50 degrees Celsius. You will try to run faster under the shadow. Similar thing happens here. If you increase the temperature, randomness increases. Because of that, velocity of the gas particles increases. Because of that, viscosity increases. And similarly, mathematically, I have explained that from the kinetic theory of gases, kinetic energy is half mv square, and it is also 3/2 kT. So V RMS is directly proportional to temperature. With the increase in temperature, velocity increases, and viscosity of the gas also increases. Clear now? Or any doubts? Is it clear? Who will ask the
Yes, sir.
question? Saurav? Now, just give me a break for it, please. I'll be back in a minute. Okay, let's come back. So again, I'll make a not access. So again, I'll make a velocity profile distribution. Okay, velocity profile distribution. So this is my velocity profile distribution looks like. This is a wall again. This is wall. So, and this is vertical direction y, suppose. Okay. So this is a direction till y from the plate or wall, and this is adjacent layer is at a distance of dy. So the fluid layer 1 is this, which is at a velocity u, and fluid layer 2 at a velocity u plus du, u plus du. So what's happening here? I'll again make a profile. For the two layers, I'll make the profile for the two layers. So this was at u. So how much distance it has covered? The fluid particle has covered how much distance? This fluid particle from point A to point B, it has covered speed into time. Distance is speed into time. Okay, u into dt. Whereas for the above layer, the fluid has covered, the velocity was u plus du times dt. Okay. So what does it mean? It is this much is udt, and some extension will be there because this particle has moved from this position to this position, and this is nothing but your du dt. All right, du into dt. So this much distance was udt, and here this much distance was udt, but here it is, let me use another color, a small distance du into dt, du into dt. So this is some angle d phi. Eventually, it's a fluid will undergo deformation, rate of deformation. That's why. What is tan theta? What is tan? And this distance is how much? Dy. This distance is how much? Dy. This dy. Yeah. What is tan theta for this right angle triangle? For this right angle triangle, I'll make a right angle triangle in a bigger sense. I'll make the right angle triangle here. So this is d phi. This is du times dt. And this is dy. So tan of d phi is nothing but perpendicular over base. Mathematical, correct? If phi angle is very small, then tan of d phi will be d phi. We have understood this concept from mathematics. If angle is very small, then tan theta can be written as theta. For small angle, tan of d phi can be written as equivalent to d phi only. Okay. So what do we say here? D phi is nothing but du dt dy. So d phi by dt is du by dy. So rate of deformation, that is d phi by dt, is equal to change in the velocity with respect to the time. Okay. And this was only if you multiply both sides with mu, both sides with mu. This is nothing but your shear stress, mu d phi by dt, which I explained in the very first starting. Mu d phi, mathematically also I've explained. So mu d phi by dt can also be written as mu du by dy. Rate of shear deformation can be also expressed in terms of velocity change with respect to the vertical distance, dy, mu du by. So if they are not giving, they are asking rate of shear deformation, and you know that what is the velocity change with respect to the distance change, then you can get the rate of deformation and you can get the shear stress. Also, if you observe, again, I'll make a axis here first of all. I'll make a velocity profile. Okay, this is again wall, and one position is this y1, and one position is suppose this y2. So two adjacent layers are here, y1 plus dy1, and two adjacent layers are here, y2 plus dy2. Will the shear stress be same in both the layers, set of layers, or different? Tell me, please tell me. Will it be same or different? If I write this is your shear stress acting, because fluid is moving left to right, so resistance will be opposite, right to left. So this is tau, and here also some shear stress will act. This is also tau. Resistance will be there. Okay. Will the tau both equal or unequal? You have your formula above. Will the tau be equal or unequal? Please tell, guess, or understand whatever you have understood so far.
So unequal.
Why?
But because it depends on the length.
Length, correct. Because it depends on this vector dy, okay, and the velocity. So velocity here is less compared to velocity here because it is near to the wall. Velocity is lesser compared to here. Okay, so I'll explain this. So both will be different. Tau 1, tau 2. Okay. And here it will be tau wall, maximum resistance at the wall. That's why fluid comes to rest. That's why fluid comes to rest. So tau wall here will be mu du by dy. There is no change in the velocity. So it will be 0 at y equal to 0. No change in the, sorry, maximum change in the velocity between this and this. It is 0 and some velocity. Maximum change in the velocity. And I'll explain with the concept of slope also. Don't worry. Okay. Whereas here tau will be mu du by dy at y equal to y2. Here will be mu du by dy at y equal to 1. Okay, y equal to 1. Let's take an example. Then you will get a more essence of the flavor. So suppose you have a velocity profile, something like this given 3 by 4 y minus y square. You are given the fluid viscosity is 0.84. Okay. And it is said that shear stress at position x is equal to 0.3 is n times shear stress at the position x is equal to 0.2. You need to find the value of n. Find n. Take a minute, think how you will do. You have the formula tau is equal to mu du d phi by dt is equal to mu du by dy. Every term is given to you. Just have to differentiate. Tell me what is the value of n. Tell me what is the value of n. Immediately solve. Immediately solve and tell me what is the value of n. Solve this question. Anyone has done? First of all, tell me what is du by dy? What is the expression for du by dy? Please don't hesitate to speak. It's a basic mathematical differentiation. What is du by dy?
So
U
3
is
by
given
4,
to you.
3 by 4
3 by,
minus 2y.
correct. So du by
3
dy
by
is 3 by 4. I'll not write like this. I'll write very basic. D by dy of u, that is 3 by 4 y minus y square. So that is 3 by, differentiate with respect to y minus 2y. Correct? Now the du by dy is this much. What will be tau? Tau is mu times du by dy. This is the formula which we have used above. And it is said that when y is 0.3 or x is whatever you write, let me write here y so that you don't get confused. Okay. If y is 0.3, then shear stress is n times of shear stress at y at point. Just you need to put y as 3 by 4 minus 2 into 0.3 is equal to n times, and this is mu into 3 by 4 minus 2 into 0.2, right? This mu and mu gets cancelled out. So this is how much? 3 by 4 minus 0.6 is equal to n times 3 by 4 minus 0.4. Anyone has solved? What is the value of n?
sir, it
What is
is
the value?
0.428.
0.428. Correct. So what we observe that tau at 0.3 is equal to 0.428 times tau at 0.2. So mathematically, are you able to feel this? That tau at 0.3 is less than tau at 0.2. So which is near to the wall, it has more resistance, more shear stress compared to which is farther away from the wall. Clear? Shear stress is less, resistance is less when the fluid is farther away from the wall compared to the near to the wall. Now is it clear? Yes or no? I want everyone, from everyone, yes or no? Everyone please tell.
Yes, sir.
Bhagirath, did you
Yes, sir.
understood? Vikneshwaran?
Yes, sir, clearly.
Nikhil? Okay. Okay, all right. Now we have understood viscosity. Now there are two kinds of viscosity. There is a difference, two kinds of viscosities are there. Let me write the heading. Units of viscosity. Units of viscosity. So first kind of viscosity is called as viscosity, or it is called as dynamic viscosity, or it is called as absolute viscosity. If in the question it is written viscosity, or it is written dynamic viscosity, or is it written absolute viscosity, both, all the three mean same thing. And the symbol is mu. So far we were dealing with dynamic viscosity only. Okay. So tau is equal to mu du by dy. So from dimensional analysis, tau by du by dy. So tau is stress, Newton per meter square, force per unit area. And velocity has a unit of meter per second. And dy has a unit of meter, correct? Meter per second per meter. So it will be Newton second per meter square. This is your SI unit. This is your SI unit. Okay. And 1 Pascal 1 pascals is equal to 1 Newton per meter square. Okay, so what will be the unit in terms of Pascal? You will have a unit of either Newton second per meter square or Pascal second. Pascal, because this is Newton per meter square is Pascal and second is left, that is Pascal second. So these are SI units. SI units. Okay. Whereas another SI unit can also be there in terms of kg. So it will be or kg per meter cube. Oh, sorry, not kg per meter cube. My bad. Kg per meter second. Kg per meter second. So all of them are in SI units. Either it will be written Newton second per meter square or Pascal second or kg per meter cube. Meter second. Kg per meter second. Okay. In MKS system, I'll just tell in MKS system also sometime examiner give. In MKS system, you can do the conversion yourself. Newton second per meter square or Pascal second or kg per meter second can be written as 1 by 9.81 kg f second by meter square. This is your conversion. Newton second per meter square in terms of. In CGS system, we have done SI system, MK system. In CGS system, 1 gram per centimeter second is nothing but poise. Is nothing but poise. So 1 poise is nothing but equal to, in terms of SI, 0.1 pascals. So if it is written, fluid has a viscosity of 1 poise, that means it is 0.1 pascal seconds. Okay. Also, sometimes they also give in terms of dyne. Okay. So always remember, dyne is a unit of force. Dyne is a unit of force, not of viscosity. So one dyne is equal to 10 to the power of minus 5 Newton. 10 to the power of minus 5. Okay. So this is just basic conversion. So this was one of the viscosity, that is dynamic viscosity. This is dynamic viscosity. Now let's come to kinematic viscosity. Another term is kinematic viscosity. And it is represent, or other name also is there, momentum diffusivity. Either it will be written kinematic viscosity or momentum diffusivity. And symbol is nu, not mu. It is nu. NEU. We spell like that. And kinematic viscosity is nothing but comparison between two absolute properties. That is dynamic viscosity with respect to density. So kinematic viscosity is dynamic viscosity with respect to density of the same fluid. Okay. So dynamic viscosity talks in terms of two particles, two molecules, whereas kinematic viscosity talks in terms of continuum. Okay, as a whole. That's the difference in the physical sense. To just give you a flavor of visualization. Yeah. Okay. So it is a comparison because this is also absolute property. This is also absolute property. So it is a comparison. Between these two absolute properties. two absolute properties. What is the unit of dynamic viscosity? Oh, kinematic viscosity. So you know unit of kinematic viscosity. Just now we have done. It is kg per meter second, and density has a unit of kg per meter cube. So it is meter square per second. So dynamic viscosity has a unit of meter square per second in terms of SI. This is SI unit. Okay, this is SI unit of kinematic viscosity. In terms of CGS system, it will be written like in terms of Stokes. So 1 meter square per second, 1 meter square, that is SI unit, or only meter square per second, is nothing but 10 to the power of 4 Stokes. 10 to the power of 4 Stokes. Okay. Let's take an example. Let's take an example. So examples is something like this. At 20 degrees Celsius, viscosity of water is 1 centipoise. 1 centipoise. That means it is 10 to the power of minus 2 poise, because centimeter is 10 to the power of minus 2 meter, right? So it will be 10 to the power of 2 poise. And 1 poise is how much Pascal seconds? 0.1 Pascal seconds. So it will be 10 to the power of minus 2 into 0.1 Pascal seconds. So unit conversion is a very confusing thing. Sometimes you have to, just it's a thing of memorizing the unit conversions, because examiner will give you in these terms. So it is viscosity of water is 10 to the power of minus 3 Pascal second. Standard value. Mu of water is 10 to the power of minus 3 Pascal seconds. You can even remember this. Okay. Whereas viscosity of air, it is given as 2 into 10 to the power of minus 5 Pascal second. So if you take the viscosity of air to the water to that of air, mu of water with mu of air, it is 10 to the power of minus 3 divided by 2 into 10 to the power of minus 5, both in the same units. It is 50. So you can understand that water is 50 times viscous than air. Water is, because you don't feel, you are sitting in a room, you don't feel viscous nature of the air. You don't feel that much viscosity. But when the air is humid, you feel very high. If these are rainy days, if you observe, you feel a lot of sweating because water has emerged inside the air. That's why viscosity increases of that. So mu of water is 50 times mu of air. So this is dynamic viscosity I'm talking about, not kinematic. Dynamic viscosity of water is 50 times dynamic viscosity of air. Okay. Another kinematic viscosity. So this was first. This is second. Kinematic viscosity is nothing but dynamic viscosity of water to that of density of water. Okay. What is kinematic viscosity of water? Just now we did 10 to the power of minus 3 Pascal second. What is density of water? 10 to the power of 3 kg per meter cube. So it will be 10 to the power of minus 6 meter square per second. Unit is meter square per second. So kinematic viscosity of water is 10 to the power of minus 6 meter square per second. Similarly for air, let's do. Kinematic viscosity of air is dynamic viscosity of air to that of density of air. So it is mu of air is how much? 2 into 10 to the power of minus 5 Pascal second divided by density is 1.2, near about 1.2327. So it will be 1.67 into 10 to the power of minus 5 meter square per second. Now let's do a ratio. Kinematic viscosity of water, that of kinematic viscosity of air, is 10 to the power of minus 6 divided by 1.67 into 10 to the power of minus 5. So this is 0.1 by 1.67. So it is less than 1, less than. So you can say that kinematic viscosity of water is less than kinematic viscosity of air. Why? Because density of water is higher, and kinematic viscosity is dense. Dynamic viscosity is that of kinematic viscosity density. So you saw that dynamic viscosity or absolute viscosity was 50 times higher for the water, but kinematic viscosity is less than kinematic viscosity of air. Is less than kinematic viscosity of. Is it clear? Any doubts? Please say something. Due to density of water is greater than density of. Any doubts, please? Don't hesitate. Yes, no, something, please say. Or I'll call the names then, please. Suryansh, any doubts?
No, sir.
Karthike,
No, sir.
no doubts? Okay. All right. So I think it is pretty much clear and fundamental topic to understand. And don't worry about these notes. I'll share these PDFs. You will get the Excel from the NPTEL mail from an Excel sheet from the NPTEL team for sure in a day or two, where the link of the recordings, because this session is recorded on and will be uploaded on my YouTube channel, and that link will be shared with you. As well as I'll share the Google Drive link where you can directly access this PDF notes, as well as in my video description on the YouTube also I'll post that link. My YouTube channel is, if you want to be regular, you don't want to wait for NPTEL team to mail you. So my YouTube channel is NPTEL with Varnit. Okay, this is my YouTube channel. You can search it, and already 2 courses have been done in the past 1 year. Yeah, all the NPTEL. So any doubts related to the course, that how some course will go on, or you have any doubts related to assignment? If you are doing the assignments, you are watching the lecture videos by the professor. So anything you have, you can ask me at any point of time. Yeah. Don't hesitate. I wish that everyone should be regular. Initially, the strength is always higher, but with time, students do come, number get less, because they have their own examination at their university level. I can easily understand. But this course is important. And if you have enrolled for this course, that means you are more serious than the other candidates eventually, compared to your batchmates. That's why you are taking a help and a proper guidance in this form. And this will eventually help you if you will be very, very regular. Take out your time. Please be attentive to these live tutorials which I'm taking. I will try to cover whole of the fluid mechanics from my perspective. So in 12 to 13 weeks. So first week has completed. Every week we are meeting from 6 to 8 p.m. on every Tuesday. And if in unforeseen conditions, if I have any change, NPTEL, you will get a mail from the NPTEL with the schedule, postponed schedule or prepone schedule, depending on the availability. Don't worry about that. But I try my best to cover up the whole course within 13 weeks, 12 to 13 weeks. You just be regular to your assignments. Ask me questions. And I feel that you won't be having any doubts after understanding this lecture turn by turn. Okay. And those who joined late, please try to be on time. I don't want anyone times to get wasted. I'll start sharp at 6 p.m. every Tuesday. All right. Yeah, Karthik, you are unmuting. Please say.
Sir, I have a small doubt regarding viscosity change due to the temperature rise.
I'll discuss.
Sir,
That is the next. Actually, that is the next topic I'm going to do. But yeah, go ahead. Viscosity change with the temperature. What is your doubt?
Sir, the density of the air decreases when the temperature increases. No, sir.
Yeah.
Sir, if the density increases, why the viscosity is decreasing, sir?
Which viscosity? Kinematic or dynamic?
Sir, no, sir. Absolute
Absolutely not
viscosity.
decrease. Absolute is dynamic viscosity, mu. That will increase.
Sir, but you told with increase in the temperature, the air in the air case.
Okay. You are saying that with the increase in temperature, dynamic viscosity will increase, and kinematic viscosity. What will happen to the kinematic viscosity? I'll discuss in the next session. Don't worry about that. That will also increase. Okay.
Okay, sir.
At a constant pressure, you have, because there are two things: pressure and temperature. So far here I was dealing with, if you see here, I was saying the term viscosity. That was dynamic viscosity. I was not mentioning, I didn't mention till here anything about the kinematic viscosity. Now you are able to think, because kinematic viscosity is a dynamic viscosity, that of density. And you understood that density increase or decrease with the increase of temperature, then what will happen to the kinematic viscosity? So you are thinking in that sense. So that is the only next topic: effect of temperature and pressure on the viscosities, both kinematic and dynamic. So I'll discuss that thing, the first very thing, in the next lecture. Any other doubt?
Thank you, sir.
Yeah, any other doubt? So as you know, my name is Varnit Kapoor. I'll be this class notes. Yeah, I'm just saying that I'll provide this PDF. You will get the mail from the NPTEL team, or I'll upload my video, and in the group description on my YouTube channel, you will find the link for the Google Drive. Okay. So I was saying that my name is Varnit Kapoor, and I'm from IIT Delhi. I'm pursuing my PhD here, and I'll be taking up this course for the fluid mechanics. And I think there are 3 TAs. The other 2 TAs are from different varieties, and they have different timings. But if you have joined in my batch, I request you that you be stick to this batch and we stick to the timings. All right. Okay. So I can stop the recording, and we can end the session, I think. Okay. All right. I'll